Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and many others on my channel. What are we doing today? We're doing multivariable calculus. This is chapter 1, partial derivatives. Coincidentally, we're New York, New York. We're also in section 1.3, which is also partial derivatives. 1.3 partial derivatives appear early in this chapter. We're not done this chapter. They appear early because these are the tools that we're going to use for everything else coming up. We need to know the rate of change of a function of more than one variable in each direction. Today, luckily, in this lecture, all we're going to do is a bunch of examples of partial derivatives of a function of two variables, f of x, y. Let's get to it. Example 1. We want to find the partial derivative of f with respect to x and the partial derivative of f with respect to y if we're given this function of two variables, which is coincidentally a polynomial in two variables. Every term is product of x's and y's of integer powers. How do we do this? Now, before I start, last time I used the definition. This time I'm just going to use the clever trick of what they always point out is when I calculate the partial of f with respect to x, I'm just holding y as a constant. So it's just acting the same as 7. If there's just a y in the term, the derivative with respect to x is also 0. Or if we're going to take the derivative of this term with respect to x, is just going to be 2y. Y is now just a number. It's weird at first, but when I take the derivative with respect to x, I'm pretending y is a constant. Therefore, the partial of f with respect to x as a function is equal to the partial with respect to x of 3x squared plus 2xy plus 3y squared minus 7. For linearity, I can distribute that onto each one if you want for the first time. You don't have to do that, but let's do that just to show you pedagogically. This is the partial with respect to x of 3x squared plus 2 times the partial with respect to x of xy plus the partial with respect to x of 3y squared plus the partial with respect to x of negative 7. Technically speaking is what my mind sees. Now that I've done that, if it's a regular function of x, just a function of x, I can take the partial and treat it as a regular derivative. So this is going to give me 6x. When I have x's and y's in the terms, I can still pull constants out, but now I'm pretending y is a constant, so he could have come out of this too. This will be 2y. The derivative of x is 1. Here, as soon as you have a term that just has y's in it, gone. It's 0. So I don't usually write those. There's the derivative. This says the partial derivative of f with respect to x is 6x plus 2y. Now for the partial derivative of f with respect to y, we do the same thing. We hold x constant and differentiate y. For this one, we've got the partial derivative of f with respect to y is going to be the partial derivative of this thing with respect to y. I won't break it up this time. Any term that has just an x in it is gone. Anytime we have y's, we hold x as a constant. This gives us 2x plus, bring the 2 down, 6y. This is the partial derivative. This is how easy it is once you know what the game is that we're doing. I'll start getting the functions harder, and then you'll be like, oh, and I have to take derivatives. So derivatives aren't always easy. So to recap, the partial derivatives of f with respect to x and y are these two functions, 6x plus 2y and 2x plus 6y. Okay, example 2, we're doing the same thing, find the partial derivatives. This time, I want the partial derivative of f with respect to x. That is going to be, again, I have a function of x and a function of x, so I'm going to use the product rule. If I take the derivative of x, that leaves me with sine xy held alone. And then plus, I'm now going to leave x alone. I'm going to take the derivative of sine xy, which is going to be cos xy times the derivative of the inside by the chain rule, which will just be y. And so if you want to clean that up, that says that the partial derivative of f with respect to x is equal to sine xy plus xy times cos xy. How clever. The partial derivative of f with respect to y now is going to be equal to, now this doesn't have any y's in it, so there's just one function of x that's a constant. So I have x times, that's a number I'm leaving on the outside, and the derivative of this is going to be what? Cos xy again, but times the derivative of the inside with respect to y, which is going to give me x again. So this will equal the partial derivative of f with respect to y is x squared cos xy. There's the partial derivatives. Next question. Okay, example 3. Let's do another one. The partial derivative of f with respect to x is going to be the partial derivative of this hot mess, which I'm going to write as x squared minus y squared times x squared plus y squared to the minus 1. So I don't have to use the chain rule or the quotient rule. I want to use the chain rule. Doing that, I'm holding y as a constant and taking the derivative of x. When I do that, the first term I get 2x times x squared plus y squared to the minus 1. Plus, now I'm going to leave this one alone, which I forgot the first try. Editing is magic. Times now negative 1 times x squared plus y squared to the negative 2 times the derivative of the inside with respect to x, which is 2x. I like this more, but no one else does because they don't like factoring. Now we have to pull out the lowest powers of everything appearing. I have 2x in both terms. Check, check. And I have, oh, everything's falling off. We have x squared plus y squared to the power of something in both terms. So we pull out the lowest power in both cases. This is equal to, I can pull out 2x. And then I can also pull out x squared plus y squared to the negative 2. Now what's left? In this one I took this out, and this one is exponent negative 1 minus minus 2 gives me a positive 1 exponent. X squared plus y squared. Plus, now here I pulled out the 2x, I pulled out all of this. This is actually, because of the minus, minus x squared minus y squared. Those cancel, the negative goes onto both terms, and this becomes a double up, and this becomes 2x times what's left on the inside in here, 2y squared over x squared plus y squared to the 2. Exponent comes positive when I pull it across the division sign. This is 4x y squared over x squared plus y squared squared. There's the partial derivative with respect to x. Let's see if we get an awfully similar pattern when we do it with respect to y. Possibly, but there's a negative on y here and not on x. Let's see. Okay, let's continue. Now you can see always with calculus, especially when we start doing multivariable calculus, not only do you have to now do integrals and derivatives of functions of more than one variable, x and y and z eventually, but we're going to make the functions harder and harder, so we can always make the functions more and more difficult because there's infinitely many different kinds of functions. Let's take this hot mess and take the derivative and the rate of change with respect to y now. We're holding x constant. X is constant. This gives me equals, by the product rule, the derivative of the first one is negative 2y times x squared plus y squared to the negative 1 left alone. Then plus, I'm going to leave this alone, x squared minus y squared. And then I'm going to take the derivative of this, and that's the same as last time, so I'm not going to annotate it. Well, I will. Negative 1 x squared plus y squared to the negative 2. It's directly connected to my brain anyways, and then we're going to get 2y this time. What does that give me? Same thing. I have 2y in both terms, and I have x squared plus y squared to the negative exponent in both terms. I'm going to pull the lowest power out. That gives me, I have negative 2y, so I can pull that out. Negative 2y, x squared plus y squared to the negative 2. What do I have left? Minus minus gives me x squared plus y squared. And then I get plus what's left here, just this, x squared minus y squared. There it is, gone. I get 2 of those. What is this? This is negative 2y times x squared times or over x squared plus y squared to the 2. I brought the exponent down to make it positive, and combining, oh no, there was 2 of them. And this is negative 4 x squared y over x squared plus y squared. Let's recap that, and then we'll do a couple more. Okay, as a recap, the partial derivative of f with respect to x is this thing, 4xy squared over x squared plus y squared squared. And you'll see eventually why we like polar coordinates and spherical coordinates. This is a circle, x squared plus y squared, and that just becomes r squared, and that would just be an r4. It's a whole lot better. Can you go, cat scratching at door, can't get in, please, I'm nervous. And the partial derivative with respect to y is this guy. Notice that they sort of interchange roles. Here I had x and y squared, and here I have x squared and y, and we got a negative. Y has a negative, x doesn't. Next question. Cat's safe now. Was it the white cat? White devil. Sorry, we had to pause. We'll put that in there cleverly, but she was harassing at the top door trying to get in to the house, so we had to stop the video, and she's being awfully purry snuggly. You can't hear it, but the full motorboat is going. I know, everyone likes you. You're the star of the show. This is Jasper. She's going to help me take the partial derivative. Can you do this one-handed with a cat? The partial derivative of f with respect to x is the partial derivative of this. Now remember, y is a constant. It's like a number. That means that we get y, x to the y minus 1. It's a number. The partial derivative of f with respect to y now is that's a to the x in your mind you have to see. So this is x to the y, and this is the constant x, this is the base. The power, this is going to be x to the y, ln x. There's the partial derivatives. Let's do one more. I know, snuggle break. Okay. When a cat says snuggle, you have to stop. It's a rule. We're shooting videos. Okay, when are we done? Okay. I know it's like 10 seconds at the end of the video. You're so cute. Oh. Okay, one more, slightly different kind this time. Just when you thought, oh, I got these partial derivatives in the bag. Watch this one. So what this one's doing is it wants us to find, remember, every time we do this, z is f of x, y. It's the same as we used to write y is f of x. And then eventually we wrote w is f of x, y, z. And then we run out of variables, so then we index. This one wants us to find the derivative of z with respect to x, the partial derivative. But now z is not an explicit function of two variables x, y. It's an implicit function in an equation of 3 variables. So we're going to play the implicit function game of calculus of one variable. We have to hold y constant while we do that. So when we take the partial of z, z is a function of just x, we're pretending. So we use the chain rule for a function of z with respect to x. Let's do that. The partial derivative with respect to x of the whole equation now is what we're doing. Again, at first when you do that implicit differentiation, break that, use the linearity of the operator partial derivative with respect to x. It is. I can write that as the partial with respect to x of yz minus the partial with respect to x of ln z equals the partial of x with respect to x and plus the partial of y with respect to x. That x got bad. Let's try that again. I've got the del operator symbol now and I can't do x anymore. Okay, good. From this, we see that now y is a constant and z is a function of x. So this is y times the partial of z with respect to x. In this term now I have z as a function of x and then it's composed with log. So this is minus 1 over z is the derivative of log times the partial of z with respect to x. Now equals, this one is going to be okay, 1. We're trying to shoot videos here. Make sure you turn all your stuff off. You've won a trip to Florida. Plus, we'll keep that in. Technology. Florida's trying to sell me, yeah, some telemarketer, I'm going to guess. Now, this one is a big 0. From there, what do? Now I have to solve for the partial of z with respect to x. Let's move that up. Now from here, just like we did in the regular implicit differentiation, you get the partial derivative, or you get the derivative of y with respect to x, and then you solve for that guy, y prime. This time it's a little bit more complicated, but now we have to solve for what we wanted, this guy, dz dx. Doing that, what do I want to do? I want dz dx on one side and everything else on the other side. Luckily, it's in both terms already, so I'm going to factor it out. That gives me dz dx y minus 1 over z is equal to 1. Depends on how you want to algebraically do this. I really want to Pavlovianly just get a common denominator and do that first before I invert it. I was sitting there having a choice between whether I divide by that thing and then get it, or I'm just going to get a common denominator first. Doing that quickly, I have the partial of z with respect to x times, now, zy minus 1 over z equals 1. And for me, I like that because now I'm going to divide by this and it's just going to go upside down. That tells me that the partial of z with respect to x is equal to z over, no, zy minus 1. Please subscribe right here and hit the notification bell. You'll get notifications for this series and many others on our channel. I'm Adrian, the Tutor Wizard. See you next time.